Okay, next we're going to look at the area enclosed by two parabolas. So this example, we've got two parabolas, one of which is given by y equals x squared, so that's just the standard upward facing parabola with vertex at the origin. And then we've got y equals 2x minus x squared. That's a parabola as well. The leading term, technically, is the negative x squared, because that's the dominant term in terms of the highest exponent. So because the x squared term is negative, this is actually a downward facing parabola. So that's going to become important later. But for now, we just got two parabolas, right? We're trying to find the area enclosed between them. So, well, what are we going to do? Well, the formula that we talked about on the previous page is right here, right? We take the upper function, we subtract the lower function, and then we integrate from a to b, where in this context, a and b were the left and right endpoints of the region we were trying to measure, or the x-coordinates of the left and right endpoints of those regions. So that kind of doesn't seem to immediately apply here because we weren't given left and right endpoints, and we're not told which one's the upper function and which one's the lower function. So it's probably best to get a sketch here. So let's start with that. Let me just draw the xy plane. And we'll just get a rough sketch. It doesn't have to be perfect, right? But just enough to be able to tell what region you're actually measuring for area. So let's start with the easy part, y equals x squared, right? That's just the upward facing parabola with vertex at the origin, so it's going to look something like this. Doesn't have to be perfect, but just an upward facing parabola, right, with vertex at the origin. And then this one here, y equals 2x minus x squared. Well, what's that one going to look like? Well, we already mentioned that it's downward facing. Pardon me, it's already downward facing, so well, it'd be nice to know where it hits the x-axis, and that's actually going to be our best bet for getting a quick sketch here. So let's check out the x-intercepts of this parabola here. So how are we going to get that? We'll just set 2x minus x squared equal to 0. So what happens? Factor out an x, and you get x times 2 minus x is equal to 0. And that's great because that tells you that the x-intercepts are 0 and positive 2, because those are the two values that would make the left-hand side of this equation equal to 0. So, well, if I label this as 2 on the x-axis, and we know it's a downward-facing parabola, and it goes through the origin as well as this point on the x-axis. So these are the two x-intercepts, and it's downward-facing. So, well, let's just do a rough guess. Something like this will work just fine. And now you have a region. Right now it's clear that there actually is a region bounded by these two parabolas. It's this region in here, this narrow piece. That's the area that we're actually trying to calculate here. Okay, so what we do have now is we do know what the region is, but we also know what the upper and lower function is. Right? The upper function on this region is actually the downward facing parabola. So the 2x minus x squared, this is actually going to be our upper function. And then the lower function down here, the lower boundary for the region, is actually the upward facing parabola. So that's how we can start our area calculation. We can start by setting that up. The area is going to be equal to the definite integral. And we'll worry about the endpoints in a moment. But the function, we're going to have an upper function, which is 2x minus x squared. And then we're going to subtract the lower function, which is x squared. Now, what about the endpoints? What is the x-coordinate of the leftmost point in this region? Well, the leftmost point that forms this region here is actually the origin, right? That's where those two parabolas intersect. That's where the region begins. Anything to the right of this point is now where this space in between them is going to start to have some area. So this is our left endpoint, or in particular the x-coordinate of this point, which is 0. The x-coordinate of the origin is 0, is actually our left endpoint. Now for our right endpoint, what are we going to do? Are we going to take 2 as our right endpoint? That might be a guess, but you can see that's not going to give us what we want. That's not the right endpoint of the region we're trying to measure. If anything is the right endpoint, it's going to be this point here. It's going to be the place where those two parabolas intersect. So this one we could just eyeball. right? We could see that they intersect at the origin. We saw that the origin was one of the x-intercepts of the downward-facing parabola, and the other parabola was an upward-facing parabola, so we knew it goes through the origin. So that one you can just look at it and tell, but for this one, we probably want to find it carefully. And this is going to be a standard approach. When you're trying to find the left and right endpoints of a region, like in our last example, they were given to us, right? We were given x equals 0 and x equals 1. We were given the left and right endpoints of our region as vertical lines forming a boundary. But in many cases, that won't be the case. You'll have to actually find them. So this is one of them. So let's find the x-coordinate of this intersection point. So let's just find where these two functions are equal. For what x values do these two functions give us the same thing? So in other words, let's solve the equation. So I'm going to put endpoints here, just to show that that's what we're doing over here. We're going to solve the equation x squared is equal to 2x minus x squared. So you can solve this however you like, but my suggestion is to move everything over to the left-hand side, and what you're going to get is 2x squared minus 2x is equal to 0, and if you factor out a 2x, you'll get 2x times x minus 1 is equal to 0. Well, and now you can just say, okay, well, when either x is equal to 0, that's going to set this to be 0, so the whole thing will be 0, or when x is equal to 1. That's the other place where the left-hand side will be equal to 0, so we'll have x is equal to 0, or x is equal to 1. So for x equals 0, that's the origin. We already knew about that one. But for x equals 1, that means the x-coordinate of this point is actually a 1. So we can label that on our picture, and now we can go ahead and put that. That's actually going to be the upper endpoint of that definite integral. And now we're ready to go. We're ready to find the area. So let's finish this calculation off. So if I clean this up a little bit, I'd have the area from 0 to 1 of 2x minus 2x squared with respect to x. Okay, so that's just combining those last two terms. Just these are combined. And then what are we going to have? Well, let's find an antiderivative for 2x minus 2x squared. So we'll have 2x, we'll use x squared, right? Antiderivative for 2x is x squared. And then for 2x squared, if you do the power rule on x squared, you'll get x to the power of 3 over 3. And if I multiply the 2 back on, what I'll end up getting is I'll get minus 2/3 x to the power of 3. And if you're ever unsure, just double check. What happens if I differentiate this term? That 3 is going to come down in front. It'll cancel with this 3, and I'll just be left with a 2 in front of the term. And then when the exponent decreases by 1, I'll have x squared. So I just have 2x to the power of 2, which is exactly what you have here. So that's how you know that that worked. Okay, and now just plug in your endpoints and subtract. So what we'll have here, we'll plug in 1, we'll get 1 minus 2/3, because 1 squared minus 2/3 times x cubed, that's just going to be 1 minus 2/3. And if you plug in 0, well, 0 squared is 0. 2/3 times 0 cubed is also 0, so really it's just 1 minus 2/3. So the area is actually 1/3, because that's what you get if you subtract 2/3 from 1. Okay, and that is now, so that 1/3, that's the area of this region that's bounded between those two parabolas. So the key thing, the key thing is a sketch, right? Just a rough sketch if possible, just to get an idea for what region you're actually measuring. It doesn't have to be perfect, right? But if we didn't know what region we were measuring, we wouldn't be able to identify, first of all, which function's the upper and the lower function. That was key for setting up this integrand, but also to figure out which points are going to give you your endpoints, right? The 2 points of intersection that we have here, that's how we knew, or these 2 points are what told us what our bounds of integration would be at this step. So that work was down here to find the x-coordinates of those endpoints. Okay, so another example that I want to show you, and this can happen sometimes, and quite often it will. I'll wait until we get into the question before I really emphasize the key feature here. But what are we asked to do? Find the area of the region bounded by the curves y equals sine of x, y equals cos of x, and then our two x bounds are 0 and pi over 2. Now at first this might seem like it's actually going to be easier than the last one, because, well, what's the difference? We're actually given our x values as left and right endpoints. So that seems pretty good. Maybe we don't even have to do a sketch, you might be thinking, right? If we already know what the endpoints are, we're given them in the question, maybe we can just use one of these functions for the upper function and one of them for the lower function. Well, maybe it's not quite that simple. And how do you know if it's that simple? The best thing to do is just to draw a sketch. It does, like I said, it doesn't have to be perfect, but it should give you a general idea of how these functions relate to each other on the interval of points that falls between these x values. So we're going to start with a sketch again here. And we only need to sketch the graphs of these functions between 0 and pi over 2. We don't have to get too carried away. So I'm going to put a pi over 2 there. There's our origin. And let's just draw a rough sketch. So let's start with sine of x. Well, sine of x starts at the origin and increases. And then right at pi over 2, it hits a maximum of positive 1. That's what sine of x does between 0 and pi over 2. And then cosine of x does the opposite, right? It starts up right on the y-axis at the point 1, and then it works its way down, and it actually hits a 0 at the point pi over 2. So cosine of pi over 2 is actually 0. So that's what the behavior is of the functions sine and cosine on the interval of points between 0 and pi over 2. So let's just draw kind of a sketch of the 0, the line x equals 0 and the line x equals pi over 2 here as well. They're going to go up, and this one's going to go down on either side. Right? This one is kind of right on top of the y-axis, but I drew it just a little bit to the left so you'd actually be able to see it. But that's actually our area. Now, what are we measuring here? Are we measuring this area? This looks like a bounded region, but it's deceiving because the x-axis was never mentioned as a boundary for this region. It was just sine of x and cosine of x. So this x-axis is just there for reference. It's not actually a boundary. So this region here is unbounded. It just goes on and on and on forever because these two vertical lines go forever. Right? Go forever in the up and down direction, and this line's going to go forever in the up and down direction. So this region here is unbounded. It goes on forever. This region over here is similarly unbounded. It goes on forever. The only bounded regions here are these two. There's one right here and one right here. So which one is it? Whose area do we calculate? The left one or the right one? And the answer is both. If you're asked a question like this to find the area of the region bounded by the curves, and you're given some curves, well, you might have several regions, right? And that's what's happening here. We actually have two regions because of this point of intersection. There's an area for this piece and an area for this piece, and we need to calculate them both. Okay, let's start by giving them names. Let's call this one A1, and we'll call this one A2. And then we can just calculate them separately, and then we can add them together. Once we find the two areas separately, we can just add them together to get our answer, which is the area of these two pieces, both of them included. So let's work them out one at a time. So let's start with A1. And here's another reason why it's so useful to have a sketch, because if we look at this region just on its own, you can see which one's the top function, right? The cosine of x, that's the upper function because it's the top, it forms this top boundary up here. So that's going to be our upper function is cosine of x. And then this bottom function here, this is actually the sine of x. This forms the lower boundary for that region. So what we're going to do is we're going to take the definite integral, and again, I'm going to leave the endpoints blank for just a moment. We're going to take the definite integral of cosine of x, because that's the upper function, minus sine of x, which is the lower function, and we'll integrate that with respect to x. Now our boundaries, we're not going to take x equals 0 and x equals pi over 2. We are going to use 0 though, because 0 is the left boundary of that region. But what is the right boundary? It's not pi over 2, because that would include this over here. It's whatever the x-coordinate is of this point, whatever that x-coordinate is. So I could put a question mark here, but why don't we just find it, and then we can put the actual value there instead. So is it going to be right halfway in the middle? That might be a bit of I mean, it depends how you want to approach this. But let's just solve for it carefully and be safe. So we'll just find out when is sine of x equal to cosine of x. Because here's the thing. A lot of people, I get asked this every year, and this is a video, so no one can ask it now, but I'm sure somebody who's watching this is wondering, well, why don't we just calculate one of these areas and double it? Right? Because it certainly looks like the other area is the same. It looks, but my drawing's not very good, but it kind of roughly suggests that these two shapes might have equal area. So do they have equal area? Well, how about we just calculate them separately, and if they're the same, then we'll know the answer is yes, and they do have equal area. But it would be I think an unfounded assumption at this point to just assume that the two areas are equal. Because what if we're wrong? If we assume that these two areas are equal, and then we just calculate A1, get an answer, and then double it, well, then our solution would be wrong. Because if we assume that they're equal and they aren't, then our answer will be wrong. So let's not make that assumption. Let's calculate each of these areas separately. So we are going to need to know what the x-coordinate at this point is, and we can get that by just finding out when is sine of x equal to cosine of x. That's the reason for studying this equation now. And how do you solve it? There's a few different ways. You can just look. You can look at the unit circle and figure out which angles give you the same value for sine and cosine, or you can just solve this carefully using the following steps. Just divide both sides by cosine, and you'll get sine of x over cosine of x is equal to 1. And what does that tell you? That tells you that tan of x is equal to 1. Right? You can look at this, you can say, well, tan of x is equal to 1, and then, well, where does tan of x equal 1? On the interval 0 to pi over 2. And you can check the trig table, or you can use your special triangles, whatever method you like. But the solution you're going to get in this case is x equals pi over 4. Now that's the fundamental angle that gives you a solution to this equation, but does that mean it's the only solution? Well, no, but it's the only solution in the interval 0 to pi over 2. Right? It's the only one we only care about this range. So that means that this is indeed pi over 4. Okay, so that means pi over 4 is going to be the upper endpoint of this definite integral.